We all know the story. It's a grand narrative, perhaps the grandest one we have ever told ourselves. About 13.8 billion years ago, everything we know, everything we can see, everything we are burst forth from an unimaginably hot, dense point. This was the Big Bang. It was the genesis of space, the beginning of time, the origin of all matter and energy. For decades, this has been our cosmological creation story, the starting line for the epic race of cosmic evolution. It's a powerful and well-supported idea. But what if that's not the complete picture? What if the beginning wasn't really the beginning at all? We are explorers, and our curiosity compels us to ask the most profound question of all: what came before? The human mind has a relentless need to understand origins. We trace our family trees back through generations, we dig into the earth to find the fossilized remains of ancient life. We look to the stars to piece together the history of our galaxy. It seems only natural, then, to push our inquiry to the absolute limit. If the universe began with the Big Bang, what was the state of affairs a moment before that? The question itself feels almost forbidden, like trying to travel north of the North Pole. Traditional physics tells us that time itself began at that moment, so asking about before is meaningless. But the human spirit, the engine of science, is not satisfied with such a simple, impenetrable wall at the dawn of time. Imagine standing at the edge of a vast, uncharted ocean. The Big Bang theory gives us a magnificent map of the currents and islands nearest to our shore, detailing how our universe expanded and cooled. It explains the formation of atoms, the glow of the first stars, the grand cosmic web of galaxies we see today. But the theory is silent about the lands that might lie beyond the horizon, or even what triggered the winds that first set our cosmic ship in motion. We are now building newer, more daring vessels of thought, theoretical physics frameworks, that allow us to speculate, to model, and to wonder about that ultimate before. It is one of the most exciting frontiers in all of science. This journey requires us to stretch our imaginations further than ever before. We must be willing to entertain ideas that sound like they belong in science fiction, yet are grounded in the rigorous language of mathematics and physics. The idea that the universe is caught in an endless cycle of birth, death, rebirth. It's an ancient concept that resonates through many philosophical traditions, spiritual traditions. In Hinduism, the concept of a yuga cycle, creation-destruction, presided over by the deity Brahma. Similarly, some ancient Greek philosophers, particularly the Stoics, believed in ekpyrosis, a periodic conflagration. The cosmos is consumed by fire, then regenerated into a new cycle. These ancient thinkers, without telescopes, particle accelerators, were grappling with the same fundamental questions of origin, eternity. In the 20th century, some physicists tried to translate this philosophical idea into a scientific model. The cyclic universe theory proposed that the expansion of the universe, driven by the Big Bang, would not go on forever. Gravity would halt and reverse it, leading to contraction and a big crunch, potentially triggering a new Big Bang. Just as the old cyclic model seemed to fade, a new and more powerful idea emerged from the cutting edge of theoretical physics, the Big Bounce. This model reimagines the beginning of our universe not as a singular event, but as a rebound from a previous cosmic phase. Instead of a big crunch, where gravity pulls everything back together, the Big Bounce proposes that a previous universe contracted to an incredibly small, but not infinitely dense state, before bouncing and re-emerging as the expanding universe we inhabit today. The key to this idea is avoiding the singularity, that point of infinity where physics breaks down. The Big Bounce smooths out the beginning, replacing the violent, instantaneous bang with a more gradual, albeit extremely rapid, transition. The theoretical muscle behind many Big Bounce scenarios comes from a framework called loop quantum gravity, or LQG. This theory attempts to unite Einstein's general relativity with quantum mechanics, and one of its startling predictions is that space-time itself is not a smooth continuum. Instead, it's made of discrete, indivisible atoms of space-time, incredibly tiny Planck-scale chunks. Just as you can't keep dividing matter forever, LQG suggests you can't squeeze space down to nothing. There is a minimum possible volume. This fundamental graininess of space-time provides a natural mechanism to avoid the singularity predicted by general relativity. Imagine a universe contracting. In the old view, this continues until it reaches a point of infinite density, the singularity. But in loop quantum gravity, this process stops when the universe reaches the maximum possible density that the quantized space-time fabric can support. At this point, The quantum properties of gravity itself create a powerful repulsive force, acting like a cosmic spring. This force becomes so strong that it overwhelms gravity and pushes everything apart, triggering an explosive expansion. The bounce. Our Big Bang, then, was not a beginning from nothing, but a rebound from a preceding, collapsing cosmic state. This model elegantly resolves the singularity problem that plagues the standard Big Bang theory. There is no moment of infinite density, no point where the laws of physics break down. The universe simply transitions from a contracting phase to an expanding one. Furthermore, some versions of the Big Bounce model also offer potential solutions to the entropy problem. For instance, some theorists propose that the immense gravitational forces during the bounce phase could effectively reset the cosmic entropy, or that each cycle expands so much that the entropy from the previous one becomes utterly negligible. The Big Bounce presents a compelling, self-contained narrative, where the universe can cycle through eternity without a definitive start or finish. If the universe did indeed bounce, could anything from the previous cosmic epoch have survived the transition? The bounce would be unimaginably violent, the universe compressed to densities far beyond an atomic nucleus, temperatures and energies dwarfing our accelerators, galaxies, stars, atoms, protons, neutrons, all utterly obliterated, ripped apart by gravity, reborn as a plasma of fundamental particles, melted down in a crucible of cosmic rebirth. Yet some physicists speculate not everything is erased, matter and complex structures destroyed, but more fundamental aspects might carry over. Gravitational waves, ripples in spacetime, are incredibly resilient. Could primordial gravitational waves from a collapsing pre-bounce universe have survived the rebound and still be propagating through our cosmos today? Finding that signal would be the ultimate fossil. It's a long shot, but detectors are getting more sensitive. Another possibility: the laws of physics change with each bounce. Speed of light, strength of gravity, mass of the electron. These constants might be re-rolled during the bounce, settling into new values for the next cycle. The previous universe could have been wildly different. Maybe stars couldn't form. Maybe chemistry as we know it was impossible. Our universe might be one lucky iteration. How could we ever test this? If the laws were different, what imprint would they leave? Look for subtle anomalies or asymmetries in the cosmic microwave background, bruises or scars left from the violent collision or rebound. Detecting such a feature would be revolutionary. It would turn the cosmos into a long history of destruction and renewal. Many previous, unread chapters. While cyclic models imagine universes existing one after another in time, another mind-bending concept suggests they might exist side by side in a vast, overarching reality. This is the idea of the multiverse, and one of the most popular roots to it comes from a theory called eternal inflation. Inflation was a period of hyper-accelerated expansion that is thought to have occurred a fraction of a second after our Big Bang, smoothing out the universe and seeding the structures we see today. Eternal inflation theory proposes that this process, once started, never completely stops. It's like a cosmic foam that is forever generating new bubbles. Within this bulk, different regions can randomly stop inflating and undergo their own Big Bang events, forming pocket universes, each with its own set of physical laws and constants. Narrator. In this picture, our Big Bang was not the beginning, narrator, but rather a beginning, the moment our particular bubble universe branched off from the ever-expanding cosmic ocean. Narrator. There could be an infinite number of other universes out there. Narrator. Some similar to ours, others wildly different and inhospitable. Narrator. Our universe would be just one island in an endless archipelago of other cosmoses. Narrator. This concept radically reframes the question of what came before the Big Bang. Narrator. In the eternal inflation model, the answer is simple: more inflation. Narrator. The inflating metaverse has existed forever, with no beginning and no end. Narrator. It is the engine of creation, constantly spawning new universes. Narrator. So, before our universe began, there was a dynamic, energetic spacetime that was rapidly expanding and from which our cosmic home emerged. Narrator. This also means that other Big Bangs could have happened before ours. Narrator. They formed earlier in the timeline of the parent metaverse. Narrator. Even though each universe has its own internal clock that starts at its own Big Bang. Narrator. Like the Big Bounce, the multiverse is an untestable idea with our current technology. Narrator. These other universes are, by definition, causally disconnected from ours. Narrator. We cannot see them, travel to them, or communicate with them. Narrator. Their existence is purely a prediction of a theoretical framework.